Hello, everyone. I don't know, there was a countdown, so probably now I am visible by everyone. Okay, let me reiterate quickly. Today, I would like to talk to you about a library called QuackOSM and how you can use it to access OpenStreetMap data at scale. OpenStreetMap data is basically a giant repository of geospatial data, a domain that's often underrepresented in typical data engineering workflows. And companies and researchers are using the data that is available in OpenStreetMap in different purposes, but this data unfortunately come in a weird format that is sometimes hard to process and need heavyweight tools. So that's why I built a Python library called QuackOSM to make open geospatial data more accessible and easier to use. And I would like to give you an introduction into this library and OSM data. Okay, so first some words about me. My name is Kamil. I studied computer science and data science. Currently, I'm working as a senior data scientist, specializing in geospatial data. And as my hobby after work, I am open source contributor. I'm co-developing a Thrive library, and I'm developing free libraries myself. That is QuackOSM, Overture, Maestro, and Bivario libraries, and you can find me on LinkedIn and GitHub. Okay, with that out of the way, let me give you a quick introduction to geospatial data. Geodata comes in two flavors, vector data and raster data. Vector data is used to represent precise objects like locations, roads, boundaries, and vectors are basically defining a specific shape of a given object and some metadata related to that. While raster data are basically images. The pixels on those images represent values. With satellite images, you can see RGB values for images, but it can also be a temperature reading, altitude or elevation, a rainfall, and other very specific wavelength readings that are important in huge Earth observation space. But in this talk, I will only focus on the vector side, vector data. And what are the vector features? OGC, so Open Geospatial Consortium, created a standard on how to represent geographic features. And there are three main types of objects. Those are the points, so specific points in space. Then there are line strings, so the points connected together into a line, and polygons, so the closed line string with holes or without it. And of course, there are also multi-counterparts, so multi-points, multi-line strings, multi-polygons, and geometry collections. Next, where is geodata even used? I mentioned at the start that researchers and companies are using the data, but what specifically I meant by that? So first part is researchers, academia. The geospatial data is used in mobility simulations, in calculating urban accessibility, or creating spatial embeddings for machine learning purposes. And this is my domain. On the right side, you can see a model output that I created for predicting locations of electric vehicle charging stations. Next part is public interest, where geospatial data is used for urban planning, for disaster response mapping, or for humanitarian help. And here you can see example of a volunteer effort to map areas after Typhoon Haiyan in 2013. So basically, volunteers took satellite images and traced out which objects were destroyed after typhoon came, and that was really important for to help people where the help was needed. Next part is businesses. So basically, for stuff like site selection or for navigation and for local marketing, where you can use locations of buildings, of points of interest, of roads to create navigation software or to decide where to place your next shop, for example. And the fourth category is gaming. So basically games like Pokemon Go or City Bus Manager or 911 Operator use free open source OSM data to create maps with real data that you interact with. Okay, so what is OpenStreetMap? OpenStreetMap is an open map database and everyone can contribute to it. Basically, whole data in OSM is added by volunteers, by people who walk around their neighborhood and map each bench, each lamp post, each road, building, point of interest, shops, and their opening hours, names, and all of the stuff that came from basically from volunteers. And the data is open and free to use, and you can download it and analyze it and use in commercial use cases. If you open OpenStreetMap website, this is what you get. So basically a map, almost like Google Maps. And you can select and see each object in OSM dataset. So here I selected Natural History Museum, and you can see its exact shape and some tags on the left that define what is this object and some metadata related to that. But how OSM keeps the data? OSM uses specific data model based on three types of objects. Those are the nodes, ways, and relations. And basically, nodes are singular points in space with some latitude and longitude. Ways are the combination of multiple nodes, and they form a ordered line. And then there are also relations that combine multiple ways or multiple nodes or even relations themselves recursively. And they are usually used to define multi-polygons or polygons with holes. So basically, if we want to map those objects in OSM to exact geometries, then nodes would be mapped to points, ways could be mapped to either line strings or polygons, and relations could be mapped to multi-polygons or polygons with holes. And if you want to get the scale of how much data is in OSM database, this is from current stats for the OSM database, and you can see there are almost 10 billion nodes in the database, and this curve is still growing and growing because while I know USA and Europe is really well mapped currently, there are also other parts of the world where there isn't as much coverage, and volunteers are still updating and creating more and more elements in other parts of the world. So I think this curve will still be growing and growing in upcoming years. Okay, we talked about geometries, but what about the attributes? I talked about some tags related to objects. And how do you know if a given object is a building or a bridge? What type of road is it? Does it have a speed limit? Is it a shop? Does it have name, brand, opening hours, and stuff like that? All of this stuff is defined by tags in OSM. And there is a website called Tag Info where you can go and see specific tags and their values, for example, for buildings. Here I can see that there's almost 665 million objects in OSM mapped as buildings, as ways. I can see the distribution of values, and I can also go to the definition in something called OSM Wiki, and I can see how specific tag and value define object and how it should be used. And it's all pretty well defined. So if you need to find something, then I would suggest go to Tag Info or OSM Wiki to search for specific tag combination that would be useful for you. Okay, so we know how the data is defined, but how can you get it to use in your project? There are basically three main sources to get this data. First is Overpass API. It has a dedicated query language. It's simple to use relatively, and it's available over HTTP. Then you can download something called PBF extracts, and you can get either small extracts for single country or for a city, or you can get whole planet. But this data have to be processed to get geometries. And then there's also GeoParquet data that you can get from OpenStreetMap USA. They created a tool where you can download GeoParquet data, but only predefined layers. So not all the data, but only buildings, roads, boundaries, and I guess places or settlements. And here is the example of Overpass API, where I wrote simple query to get highways and buildings, and I can see the output on the right. And it works great for small scale. Then you have GeoFabric extracts, where you can get specific regions, download it locally, and parse them later. And there's also a website called SliceOSM, where you can trace a polygon and you will download only the data for a given polygon. And it also only works for a small scale. Okay, so now that we know how OSM data is defined, how we can access it, let's imagine a fake scenario where we want to have a project to utilize OSM data. So let's develop a game with OSM data. This game will be called Last Mile Mayhem, a tycoon-style game where we will deliver packages with trucks, drones, bikes, boats, etc., and we will build a delivery empire. So first step in game dev will be to prototype the game. So let's imagine we need the data for a single city. We do a quick Google search and we find that OSMNX is the most popular Python tool to get OSM data. So, okay, let's use it. Here is the code to get data with OSMNX. We define a place, we define some tags, so buildings and highways, and we get a geodata frame for GeoPandas library with this simple function. And yeah, we get data for the city of Sydney. Then we can do another query on top for getting post offices, shops, restaurants, buildings, and we define some delivery areas, test the gameplay loop, everything works fine, it's great. But if I want to get data for more cities, I need to run the script overnight and wait for it to finish, because OSMNX uses Overpass API and it is slow. But okay, I had time to sleep, and let's imagine the scenario where the gameplay loop is done, and now I want to make a big map. I want to have on the whole country level. So if OSMNX worked, maybe it will work again. So here is the data for the whole country. For Australia here, I mapped some cities, and this is how the data should look like on the map. But yeah, it doesn't work so easily. Unfortunately, OSMNX also works in memory, and the kernel, if I worked in Jupyter Notebook, just died, and I don't have enough memory locally to parse the data for the whole country. Okay, so let's reiterate. We'll do another search, and then we find that most popular other tool is something called GDAL. Okay, so let's try it. GDAL is like geospatial data abstraction layer, and it's very, very popular in the geospatial domain. But unfortunately, installing GDAL is not easy, and especially on Windows. You can install it if you use Conda, but I'm not Conda user, so this also goes out of the question. We do another search, and we find the library called PyOsmium. It has Python bindings, and you have to write your own logic. But without multiprocessing, you will also have to wait some time to parse the data for the whole country. So in total, OSM data is hard to read at scale in Python. If we want the ideal solution for our use case, we want to avoid GDAL or Spark or other external dependencies. I just want to run pip install and be done. Next, it should run on a single machine and it has to be fast. So I started doing some research in March of 23. How can I improve current state of working with OSM data? Then in April, there was a extension to DuckDB database called Spatial that was released. And 2 months later, Max Gabrielson, the author of DuckDB Spatial, created a function called read OSM, specifically for PBF files. And that's when I started working. And in 6 months, I created QuackOSM. So what is QuackOSM? Basically, it downloads the data from OSM in this PBF format, reconstructs geometries with DuckDB, and saves the data as GeoParquet. GeoParquet is like the current cloud native format for saving geometries, and it's really fast and can be indexed, and yeah, very good format for vector geometries. And here you can see the previous query that I used in OSM So here it is in QuackOSM. So basically, I also define a place, city of Sydney. I geocoded to geometry. I defined those tags, filter, and then run convert geometry to geodata frame and get the same result basically as OSM QuackOSM installs without any external dependencies. You can just run pip install or conda install, and it has a CLI as well. What it does is basically transform PBF files into GeoParquet format without memory limitations. DuckDB allows you to offload some bigger than memory transformations to disks. So if you don't have enough memory to parse a big data set, then it will use some of your disk space, but will get it done basically. And you can run it in CLI, QuackOSM, then I use query to get Poland, and in 20 some minutes I get parsed data for the whole country, everything that is available in OSM for the country of Poland. You've got 3 main functions in the API. You've got convert PBF to Parquet, you've got convert geometry to Parquet, and you've got convert OSM extract to Parquet. So if you have existing file, then you can use convert PBF. If you don't have existing file, you don't know what you even need to get the data, you can use convert geometry. So you basically pass a shape from the Shapely library, and QuackOSM automatically finds the data you need somewhere in the internet, downloads it locally, and then parses it for you. Or you can find a specific OSM extract with string query as well. And it also integrates with GeoPandas, so you can convert it to geodata frame, and integrates with DuckDB, so convert PBF to DuckDB. Next, yeah, the library can be run as CLI, so you've got the help function and a lot of flags for finding stuff, for filtering stuff. Basically, you can see it in the documentation. As I mentioned, there's also automatic matching, finding of PBF extracts. So I just gave it a shape, this square, blue square, to find the data. And it found 3 extracts that will cover this region, and downloads it for me, and I don't have to think about it where this data come from, but it merges everything to a single file, and I get the data for this square. You can filter the data based on geometry. So here I've got existing file and I want to only get data for the city of Prague, or ask it to get the data for Prague, and it will download it for me. You can also filter the data based on tags. So here I want to get amenity bar and cafe, so get bars and cafes. Or I can also find local ice cream shops that don't have brand defined. With OSMNX, you cannot use false value as a filter. With QuackOSM, you can use false Boolean value to find objects without a given tag. And you can also use asterisks or wildcards. So it will find like the matching string values for you with SQL in DuckDB automatically. So here I found astronomiczna wieża in Prague. Okay, so what's the dependency stack for the library? I'm using mainly DuckDB to create all of those queries to wrangle the data. I'm using the Pooch library for getting data from the internet, for downloading files. I'm using polars as well because some operations are faster in polars than in DuckDB. Of course, I'm using GeoPandas for integrating the data. I have Typer to create a CLI, Apache Arrow to wrangle the data in Apache Arrow, and GeoPy for geocoding queries. And here you can see example of a query in DuckDB where I'm reading data from Parquet and I want to find objects 500 meters from a given point. And with spatial extension, I can just work with geometries, and that's the main feature that allows me to work with OSM data. And here is the function stReadOSM, where I get some object with ID and tags and latitude and longitude, and that's how I access this data. But unfortunately, this process is really convoluted. Reconstructing geometries from the raw OSM data takes a lot of steps. Here you can see the diagram of steps that I have to do in QuackOSM to get raw data from OSM and get geometries at the end. So that's a lot of steps. And if you want to read more about it, then I have a blog post on Towards Data Science about it, and you can read there all of the steps. Okay, so let me go quickly through alternatives. Basically, I mentioned already OSMNX or PyOsmium, but there's also PyGeosm, Pyrosm, and ASI OSM Shape. And OSMNX uses Overpass, and other libraries also work on PBF directly. There's also Apache Sedona. If you want to use Spark Reader, there's a PBF file reader since version 171. And you can get GeoParquet files from Layer Cake that I mentioned in the earlier, but there are only 4 layers right now. And quickly, let me go through the benchmark. So basically, first I will tell you about processing time. So Monaco and Paris, as you can see, QuackOSM have a time overhead at the start because it makes a lot of queries. So for really small regions, it takes a long time. But with Paris, it already catches up with QuackOSM and Pyrosm. But if we go to bigger regions like Portugal or Poland, we've got memory errors or timeouts. So basically, OSMNX and Pyrosm work in memory. So if you don't have enough memory, you cannot parse the data. And with PyOsmium, as you can see, it takes like 4 or 5 times more than with QuackOSM. So it gets faster and faster with scale, basically. And if we want to compare benchmark for download size, OSMNX downloads Overpass responses and save it on file. And basically, as you can see, JSON responses take 8 more times space than a compressed PBF file. So that's another part that you can look at. And if you want to see whole benchmark, then I have a repository with this benchmark available. So to sum up, if you want to download OSM data without any hassle, you can use QuackOSM. It will automatically download the data and parse it for you without memory limitations. And quickly let me show you a real world scenario that I created from my domain. Suppose you want to create a network of electric vehicle charging stations in some city. Using open data, we can get the information from another city and use transfer learning to make predictions for another city. So that was my thesis for master studies. And basically, I downloaded the data for a single city. So here are charging stations for Amsterdam. Then I assigned some distances for hexagons on the map. And then I trained the model with OSM data and applied it to Prague. And you can use this in a planning process or as a nice eye-catching artwork in your home if you fancy. And before finishing, I would like to thank some people that I interacted along the way. So basically, first for Max Gabrielson for creating the DuckDB spatial extension, for Joris van den Bosse, who is the maintainer of PyArrow, GeoArrow, and GeoPandas, for Dewey Dunnington and Kyle Barron for their work on GeoArrow specification, and for Chris Holmes for his work on GeoParquet format and creating great resources how to work with it. Okay, so thank you for listening. You can find me on LinkedIn and GitHub, and if you found it interesting, please use the QuackOSM library, start it on GitHub, and let me know if you had any problems with it. That's all from me. Do you have any questions? I'll be happy to answer them. Okay, I see some questions on Q&A. How can I enrich the OSM models for my city? Basically, there are some methods to evaluate what tags are missing basically in a given region. So like you get the distribution, for example, of how many highways, buildings, and given tags are in other regions, and then you compare it to your region based on the area, for example, and then you can assess for what might be missing. But that's kind of you have to know a lot about OSM to do it properly. Let me show. Oh yeah, I can show it on stage. And yeah, OSM also has an editor, so you can register your account and add stuff. Basically, I don't know if that's exactly what you meant by this enriching the OSM models for your city, but yeah, you can write to me on LinkedIn if you want to specify more. And another question, once I download data, for example, for Prague, can I use the library to geo-encode addresses offline? Yes, if there are addresses defined in the OSM data. So basically, there are tags called adr and semicolon, and there you get the street number, the street name, and you can use those to extract addresses for buildings. But it's not a given that every building will have this data mapped. Okay, and another question from Hassan. Please allow me to ask this. Can I convert OSM to knowledge graph or network with nodes and edges? So basically, OpenStreetMap, the OSMNX library that I mentioned before, its main focus is to download highways and create network X graph that you can use for routing, for calculating metrics on a graph. So with QuackOSM, it's on a roadmap to extract this graph, the edges and nodes. but it's already been done in academia, and it's used, like using the highways to create a network that we can use for routing or for calculating some metrics about accessibility. Okay. Okay, so thank you for listening. I don't know if there will be someone from backstage to show another person, but thank you for listening, and I guess that's all from me.